Okay, so we're on calculating reaction rate. So once you decided which quantity you're going to measure, then you can start to collect data. And sometimes that data is going to be just in a table. Sometimes you can just collect it over time and make it in a graph, and then calculate the average reaction rate. But sometimes they're going to ask you to convert from one substance to another. And that means that you're going to be doing a mole ratio and you'll be using stoichiometry. So let's take a look at this practice problem here. It says calculate the average rate from lab data. We have a paraffin candle in a petri dish on a scale, and this is happening over 15 minutes. We're looking at the mass change. You'll notice that the mass is decreasing as the paraffin is consumed over time. So they want us to calculate the average rate of combustion of the paraffin over 15 minutes. We'll look at your initial point and your final point, and then you're going to calculate that change, which is here on the next page. It's 170 minus 180 over 15 minus 0. You're going to get negative 0.666 grams per mole. But I told you earlier we want the absolute value, so you would make this 0.666 grams per minute. And this is for the paraffin. So this is for the C28H58. It's important that you note what substance it is, okay? Then they want you to calculate the average rate of formation of water vapor over that time period. Well, we're going to need this written as a fraction. And you have to convert the grams of paraffin to moles of paraffin by dividing by its molar mass. And then you have to do a mole ratio from paraffin to water. If you look at this balanced chemical equation up here, you'll notice there are 2 paraffins for every 58 waters. So that's where they got this mole ratio down here. And then you convert your moles of water to grams of water by multiplying by the molar mass. You get 0.882 grams of water per minute as being formed over that time period. Okay. Number C, suggest a reason why the rate of the reaction isn't greatest at the beginning with a steady decrease as time passes. Well, if paraffin is burning in air, isn't there an unlimited amount of oxygen available for that combustion reaction to happen? So you're not really running out of reactant. You still have paraffin, you have oxygen in the air, and so that's why it's relatively constant over time. D, why don't the mass values drop in a completely constant fashion? Well, there is some variation in the rate, but it's due to the uncertainty in the measuring device that was being used. Okay, so the balance had some uncertainty, and that's why they don't drop the same way. Let's take a look at the next page and let's do some practice. Number 1, a piece of zinc metal is placed in a beaker containing an aqueous solution of hydrochloric acid. Okay, so you have zinc, metal, in hydrochloric acid. You're producing hydrogen gas and zinc chloride. Okay, this isn't balanced, you need a 2 in front of HCl. The volume of hydrogen gas is measured by displacement. So here they have the volume of hydrogen, and I'm emphasizing that this is hydrogen here by circling it. You may want to highlight that. They measure it every 30 seconds, so here are your time intervals. And the volume was at STP conditions and recorded. They want us to get the average rate of consumption of zinc over the entire 150 seconds in grams per minute. Well, this is the volume of hydrogen, but that is what they're asking us for is zinc. So what that means is you've got to take your 25 milliliters of hydrogen gas. I'm just going to put this here. And you want to put that over the 150 seconds, that time period here. Because that gives you the rate of the hydrogen gas that's being produced. Then what you're going to do is you're going to convert a milliliter to liters. And then we've got to also convert to minutes because they want grams per minute. So I'm just going to put 60 seconds in a minute. So that cancels. And then we've got to convert, since we're at STP, we've got to convert this liters to moles, and this is moles of hydrogen. So now what you can do is do a mole ratio from hydrogen to zinc. So we've got a 1-to-1 mole ratio. And then they want it in units of grams, which means you have to convert your zinc to grams. The molar mass of zinc is 65.38. And this is going to come out to be 0.029 grams per minute. Now, they ask us, when is the reaction the greatest? If you take a look, every 30 seconds, the volume of gas that is being produced is different. Here, we went up 15 milliliters. Here, you went up 6. This was 3, this was 1, and this was none. So what this is telling you is that the reaction is the greatest at the beginning. And then what is the rate from 120 to 150 seconds? Well, we weren't producing any gas during that time period. So here the rate is going to be 0 milliliters per second here. And then C, or D, assuming there is still a small bit of zinc left in the beaker, how would you explain the rate at this point? Well, if zinc is left, that means that the hydrochloric acid is gone, and it's the limiting reactant. It limited how much product we could produce. So that means that zinc is the excess reactant. Okay, do you want me to do one more like this? Number 2? Let's take a look at number 2. A 3.45 gram piece of marble is weighed and dropped into a beaker containing a liter of hydrochloric acid. The marble is totally gone 4.5 minutes later. Calculate the average rate of reaction of HCl and molarity per second. Remember, this moles per liter here is molarity. Note that the volume of the system remains a liter throughout the entire reaction. So you have CaCO3 solid dropped into hydrochloric acid. You're going to make calcium chloride, and then carbonic acid, which is unstable, so that means you form water and carbon dioxide. So this is from H2CO3, which is totally unstable, which we talked about in the fall. So you're making carbon dioxide gas and liquid water. Okay, so if you've got a 3.45 gram piece of marble, and it's in a liter of hydrochloric acid, and we want the average rate of reaction for HCl. You have to get from here to here. So that means we're going to be doing a mole ratio. So you're going to take your 3.45 grams of calcium carbonate, and you're going to divide it by its molar mass, which is 100.09. This equation needs a 2 in front of HCl to be balanced. So that means the mole ratio is 1 to 2. And then we need this in molarity per second. So that means that you're going to have to put this liter of hydrochloric acid, since you have moles, these all canceled. Since you have moles of HCl here, put your 1 liter of HCl here to give you a molarity. And then what we have to do is we need to incorporate our time. The time was 4.5 minutes. So what you could do is you could put your 4.5 minutes here and then convert your minutes into, they want seconds, so there are 60 seconds in a minute, and that will give you the units that you're looking for. If you multiply everything out, you're going to get 2.55 times 10 to the negative 4th molarity per second. Okay?